will vibrate along the direction of propagation. So what are these black dots? Black dots shows the direction of the vibration of a particle, and there's a wave speed. The wave is moving along positive axis. The particles will vibrate along x-axis here. So this example of longitudinal wave. What are that particles here? Longitudinal wave. The medium here, it can be liquid, solid, or the gases. That one for a longitudinal wave. Shall I call this a mechanical longitudinal wave better rather than only longitudinal wave? So can we call this as a mechanical longitudinal wave? What can be medium? This medium, particles of medium. Particles of medium. So what can be medium for the discussion? It can be solid. Solid, liquid, and gases. What was the medium for the transverse wave propagation? It was a rope. That's all. We didn't go for any other thing. Can you remember? Here, what happened for sound wave? The medium can be solid, liquid, gases. Solid means some rod. Liquid, best example, water. Gases, air, the best example. So here is what will take the medium to be all these examples. That one. Then what is the example of mechanical longitudinal wave? Means here as the wave propagates, the particles of the medium will vibrate along positive x, means the wave propagates along positive x-axis and the particles will vibrate along x-axis. I'm not saying only positive, they'll vibrate, they'll exude SHM along x-axis. This is called like a longitudinal mechanical wave. Then what is the example of this one? The sound wave. What do you mean by sound wave? I'm speaking. What all I'm speaking? Nothing but a sound wave is said to be propagated. So how to study this? How to study this? So you are speaking. Do you are able to see the sound wave propagating as a sound is moving? The point on a medium, it is moving sir towards right, is having a velocity, is having acceleration. I'm able to see. None of us can visualize that particular thing. But in fact, the wave is propagating and the points on a medium, they'll exude SHM. So now we have to bring in a method. So for that purpose, so what we do is like, I'll assume a chamber concept. So let me assume that one between my ear now there's a just initial way of showing things. Okay, initially okay, what was the pressure? Pressure, let it be P naught. Let me take example, the air itself. You are sitting in a room and as you start speaking in your room, so definitely the medium, what is the medium? The air surrounding you, that is the medium. So what is the pressure there? Atmospheric pressure. So what is the air? This everything is air. So what I'm asking is, imagine, let's imagine that we are in a classroom or like somebody, your father is speaking or your parent is speaking to you. Your parent will stand here and you are at this particular point. This one, you are at this particular point. So here, source, I'll write it. What is the source? Anybody is speaking. Don't think that something imaginary source means something. A person speaking. This one, so a person is here. So as the person speaks, that one, and other person is going to hear this sound. So between these two persons, I'm asking you to assume a pipe, a cylindrical pipe. This cylindrical pipe, you are going to break up that into chamber. These are called like a chambers. Okay, there's a person one, you say like it. So between person one and two, yeah, everything says like everything here, air is present. I'm just asking you to assume a cylinder. That one, break that. The it's a, don't assume that answer when we speak a cylinder will come. No, it's only assumption. Assume that a cylindrical air column like this. Then break up that into equal parts. That will be chamber. So what is the pressure here? Will be P naught. Density will be rho naught. Atmospheric, what is P naught? Atmospheric pressure. Atmospheric pressure. What is rho naught? Atmospheric. Mean atmospheric pressure, mean atmospheric density. We know P naught value, we know the mean atmospheric density. That one. So when this person is not speaking, so he is a speaker, either singing or a speaker, and he is going to hear. He will hear it. Okay, getting the idea now. So when this person is not speaking, what will happen to the everywhere pressure will be P naught. What is the everywhere density? Rho naught. And what happened to each chamber? It will have a fixed volume V naught. So now this person will clap when he claps. So what do you mean by clap? Like this. Or you'll say, hello, anything. So like a pulse. You go back to the transverse wave pulse, no? If I vibrate my arm up and down continuously, I'll get a sine wave. If I hold one end of the rope, if I vibrate arm continuously, see the same idea, this one. So when do we'll get situation of like this? If I give a jerk, no, am I right? If I give a jerk, it will go like this. Instead, if I vibrate my arm continuously, what do I get? So what is the thing? So just giving a jerk. What about here? If you wave your arm continuously up and down, if you just give jerk and release, a pulse is generated. If you wave your arm, if you move this one end of the rope continuously, then what happens? It will be sine wave. Same thing here. I can ask this person to speak continuously or just few words. Hello, that is enough. Hi, hi. Let's take hi. Hi, we'll see that one. Then we'll see that one. If it says I, it will be like a pulse. If it speaks kind of like, good morning, hello, how are you? How is your physics teacher? How is teaching? Maybe situation, the continuous disturbance, the medium particles will get disturbed. Okay, that one is like a pulse. This is a wave. Pulse wave only will call, but to make difference, no, we'll call this a pulse propagation. This is a wave propagation. That one. Now this person will say hi. When he says hi, he should open his mouth, no? So then what will happen here? Here the air which is present will get disturbed and it will go in. So let him stand very near to it. So the moment he says hi, or he will clap. I think clap is the best thing because loud disturbance will be produced. Like this, he'll clap it. The moment he'll clap it, no? So this person is going to hear, no? How you will hear that disturbance? So nothing much shall I say, he has generated disturbance. Earlier, the speaker and the person one, person two, they're calm. And what is the pressure? Everywhere P naught, density everywhere rho naught. The moment if he claps or he starts speaking, he says hi. What does it mean? Shall I say is it disturbing the medium? It's generated disturbance. So what do you mean by generation disturbance? Means he first generated disturbance here and the disturbance will propagate. So what will happen to this layer? This layer will undergo compression. This layer will undergo compression. Okay, the compression I'll show by some other. Now, why it will get compressed? You do one thing, take old paper in front of your mouth, start speaking. What will happen to that paper? Paper will start moving, no? I think that I'll show it. I think let me try to show this. Hello, hello, hello. I think the tip one, you can see. Hello, 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 hello. Are you able to see the tip? Tip will start moving, no? If I start playing, hello, hello. So as I say that hello, if I speak still loudly, hello, so it will start moving. Hello, hello, it will start moving. So means here, this is like some sort of a layer. Huh? There's a layer. So you assume there's like a layer in the air. So if I start speaking, this will start vibrating because the moment I speak here, no, the air molecule, the air which is there will undergo compression. So this is, let me keep paper this very near to mouth. So if I start speaking, so you do one thing. So take a very thin, like this. It'll be, hello, hello, hello. Are you able to see the tip? Because the big paper, no, it will not be. So if you take thin paper and try to see this one. Hello, hello, hello. So it will start moving, no? Why do it will move? Because when I speak, what will happen? When I speak, I'm going to displace the layer which is going to present near my mouth. This is very important. I'm going to displace the layer which is going to present near my mouth. So what is a layer? There's a layer one. There's a layer one. So here we'll give the name for this one. There's a layer one, two, three, four, five, six, seven. There's a layer one. So first it will get displaced. So it will undergo compression. So what we get it here, I think the one, two, I'll remove because I'm using some other. No, it will undergo compression. So the pressure here will become P1. What about the remaining? The disturbance is yet to reach there. The disturbance is yet to reach there. And the density will be rho naught, rho naught, rho naught, rho naught. And what is the density has become rho naught. So what happened here? This has undergone compression. So what is the pressure here? Will be more than P naught. So definitely this layer will exert force. Go back to thermodynamics. P1A minus P naught A. I'll introduce all the things what we learned, so that will be easy for you. So what is this? P1A. This is, or P1S will write. A I'll use for amplitude, no? Which will be greater. P1S will be greater than P0S. So very next moment, so this person he has just said only clapped once, not like continuously is clapping. He has clapped only once. He has said only hi once. Hi. Okay, now that hi, what happened? What he spoke hi, no, that will produce disturbance here at the chamber one. So P1 greater than P naught. Here also the pressure will be less than P naught. So here also the force will act here. So next what will happen? This has undergone compression. So P1 greater than P naught. So therefore this particular force here what will try to push it. So what it will do is it will make it to undergo rarefaction, we'll call it. some other symbol. So what we have is a rarefaction. So it will start expanding. So then the pressure here will become P2 density. What happened the adjacent layer? So now the disturbance which was there, no, now this is available. So what is one? If it says I, so it is available now. The disturbance now you can see the blue color one, it is available here. The remaining, the disturbance is yet to reach the third chamber. Am I right, sir? What is this? We are not understanding because the moment you speak, it should propagate. No, it will take some time. How the disturbance will propagate instantaneously? It needs some time, no, to propagate. Like you can see in the right diagram. So this will, the blue color one will call that as a compression, and the green color one is called as a rarefaction. What do you mean by this? If it says I, immediately will not be here. So immediately will not reach here. It has to propagate, no, the disturbance. Now, first it will be here. Next it will be here. Okay, got this one. So after this rarefaction, again, it will come back to its original situation. So this will be this layer. Now, what will happen to this one? From compression, rarefaction, again, it has become to natural. So this has undergone compression. Now this will undergo rarefaction. Let me finish off this so that this will be rarefaction. Rarefaction, there's a compression. Okay, now we'll shade all the things. Different books that have explained in different way. I felt this is a little bit easier for students to initially analyze because this is what needed for us for in numericals. That's why I just picked up this sort of explanation. The different books they have given different animations also. If you look at the YouTube, no, now you have different animations. Are there? I'll show maximum most of them. Okay, that where all compression pressure P1, density rho 1, P1, rho 1. What are these symbols? Symbols, I'll remove this one. Again, you may get confused. This represents compression. This will represent rarefaction. Rarefaction. So P1 will be greater than P naught, rho 1 greater than rho naught, P2 less than P naught, rho 2 rho naught, rho 2 less than rho naught. If the pressure greater than mean atmospheric pressure, then it is said to be compression. If the pressure in a chamber less than the mean atmospheric pressure, then it is said to be the rarefaction. Okay, are you able to understand the rarefaction? That particular condition is called as rarefaction here. And the volume of chamber more than initial volume, then it should be rarefaction. Volume of the chamber less than initial at equilibrium condition, then it is said to be compression. So what is said high? So what that high? So this is the disturbance. This one is called as a disturbance. Everything is called as a disturbance now. Don't say there's only disturbance. Here only it will come. I don't want to trouble you. The disturbance is here. Now it is here. After some time it is here, here, like this. It is propagating. It will take some time for the person to reach here. So in what direction the disturbance is propagating? The disturbance in fact is propagating like this. Let me show it here now. So this everything is one disturbance. What is the disturbance means? One compression, one rarefaction. I'll show it here like this. This is what? Disturbance created by person 1 at t equal to 0. And after some time t, it is available here. Disturbance created by person 1 person. Let's take that one. So the disturbance will propagate here. Okay, I need not to show every time. So the disturbance which was here now will be available. T equals 0, it was generated. So you can take this as t equals 0. This is after some time t. And it will take some time for the disturbance to propagate here. Am I right? If I say hello, if I say I, since you are very nearer, okay, it's gone. If you're a little bit far away, no, it will take some time, the disturbance. So what is the disturbance now? Tell me, like, who got disturbed? Person 2, person 1, shall we say, is a disturbing person 2? No, here we are not talking about the persons here, the medium gets disturbed. So what was the earlier pressure? P naught, rho naught. Okay, I agree this. As the person starts speaking, the layers here will get disturbed here. Sir, I'm not seeing layers. I'm asking you to assume. So there's one chamber. Inside this chamber, you should assume now infinite layers. So a good example, your chemistry books, which will be very thick, no? Your chemistry textbook is a chamber. The pages open, you can assume a layers. So as you start speaking, so definitely open the layers, open the different layers will undergo the displacement. So meanwhile, we are talking about only in one chamber, what happens, the pressure will vary and the density will vary. So this is called like a compression. Then rarefaction, like this compression, rarefaction, the disturbance will propagate from one end to another end. Who is getting disturbed? The medium getting disturbed. So what is this everything? This air is nothing but a medium. So as a person speaks, what happens? The medium gets disturbed here. And what do we notice due to disturbance? There'll be change in pressure, there'll be change in density, and inside this one chamber, what will happen? The different layers, they will have a different displacement. And as the wave propagates, we know it's a longitudinal mechanical wave. So the layers, they'll exude SHM about their respective mean position. So Newton long back, yes, he was able to imagine so much things. Now, what he has said that we are unable to imagine. On his own, he is able to analyze so much without any equipment, everything. He was able to think. He's a human being. Dedication, that's all he was interested. Interest and observation, these are the two parameters in science. Many students, even till date, they'll ask, sir, I am unable to solve problem. Interest and observation, finish over. Nothing is there. There's no any other thing. If you are able to solve problem, if you are unable to solve, why you are unable to solve? The interest and observation. There's the only parameter. Even you ask me after 100 years, I'll repeat same thing. Why others could not derive expression for speed of sound? Yes, Newton was interested. For him, that was everything for him, for his life. So he dedicated himself. Same thing for you also. You want a rank? Yes, dedicate. Think on it. Analyze. Put effort. That one. So that should be there, the internal. That one. Not somebody should pressurize you to do numerical. Okay, given the PP, how many you are done. Okay, you may get rank. So really you want a better rank, no? It's your desire should be there to get a better rank. Desire should be there to for you to solve problem. Then only you think. See, science and technology will not come somebody teaches. Science and technology will come only when student is interested. You learn when you are interested. Not somebody teaches, it will you learn science. Not possible. Hmm? So by time and again, I'm telling the same thing. Of course, skills the teacher will impart, but you'll grow in science and technology only if you have interest and observation. You should make observation. There's no other way. Draw the diagram, think on it. Why not like this? Why not like this? Imagine it, analyze through various ways. You'll get the answer. Okay, but such a thing is not there. You know what we want. Without much effort, we want no knowledge. That's the biggest way of blunder what we do in preparation for JEE Advanced. Means without effort much, means without much pressure, we want to acquire science. Not possible. Huh? You should not sleep. Maybe sometimes you may not get a sleep. It's good. That is what happens in science and technology. Sometimes the numerical may trouble. Huh? I may not get sleep till that answer will come. This is what happens here. So now what happened? We want to sleep happily. We want to play, we want to watch movies, then still we want a rank. How it is possible? Some sacrifice should be there at other parts, no? I'm not asking you to read 24 hours, but the surrender to science and technology is must. Without that, not possible. Huh? Okay, now we have somehow able to show that. Means now, as the wave propagates, tell me what will happen. What changes in the medium we notice? We see that as the wave propagates,